Let f be the unique function defined on the positive integers such that summation d divides n, d times f, n over d equals 1 for all positive integers n, where the sum is taken over all positive divisors of n. What is f 2023? So let's start with n equals 1. It's straightforward that f1 equals 1. And then let's consider the case n equals p, where p is a prime. Then fp plus p times f1 equals 1. Substitute f1 equals 1 to obtain fp equals 1 minus p for the primes. Next, let's try when n equals a p squared, when p is a prime, then fp squared plus pfp plus p squared f1 equals 1. And substitute f1 equals 1, fp equals 1 minus p to obtain that fp squared is also 1 minus p. Next, let's try n equals p times q when p are q are primes. Then fpq plus pfq plus qfp plus pq times f1 equals 1. Substitute f1 equals 1, fp equals 1 minus p, fq equals 1 minus q, and solve for fpq, which actually turns out to be fpq plus p 1 minus q plus q 1 minus p plus pq equals 1. After expanding terms and combining everything to the right-hand side, it's easy to see that fpq equals 1 minus p, 1 minus q. Okay, and thirdly, I'm going to try n equals p squared times q, right? And then f p squared q plus p fpq plus q fp squared plus p squared fq plus p squared fq and p squared pqf. Okay, this pq fp plus p squared q f1 equals 1. Okay, let's substitute fpq equals 1 minus p, 1 minus q, p squared 1 minus p, fq 1 minus q, fp 1 minus p, f1 equals 1. And when we just expand everything, a lot of terms cancel each other out, and we get fp squared q plus p 1 minus q. So those terms add to p 1 minus q, and then q 1 minus p plus pq 1 minus p plus p squared q equals 1. And then after expanding terms and add them up, we get fp squared q equals 1 minus p minus q plus pq. Or this indeed 1 minus p times 1 minus q. And then since 2023 equals 17 squared times 7, then f 2023 equals 1 minus 7 times 1 minus 17. And this is 6 times 16 is 96. And 96 is our answer, which is B.